Magnetism is one of the fundamental forces that shapes the cosmos. While often overshadowed by gravity in discussions about the universe, magnetic fields play a crucial role in the formation, evolution, and behavior of celestial objects, including stars, planets, and even entire galaxies. In this video, we will explore how magnetism influences these objects and the processes that occur in space. Magnetic fields are produced by the movement of electric charges, and in space, they exist in a variety of scales, from small planetary fields to those that stretch across entire galaxies. Unlike gravity, which only attracts, magnetic fields are dynamic, influencing charged particles in complex ways and often driving the behavior of matter in space. The strength of a magnetic field is typically measured in Gauss or Tesla, while magnetic fields on Earth are relatively weak, about 0.5 Gauss. In space, they can be much stronger and have far-reaching effects on everything from solar activity to galaxy formation. Stars, including our Sun, generate magnetic fields through the motion of charged particles in their interiors. The Sun's magnetic field is generated by a process known as the solar dynamo, where the movement of plasma, hot, ionized gas, and the Sun's rotation creates strong magnetic forces. These fields give rise to various solar phenomena. Sunspots. These are regions on the Sun's surface where magnetic fields are particularly intense. Sunspots appear darker because they are cooler than the surrounding areas, and their presence is linked to the Sun's magnetic cycle, which peaks roughly every 11 years. Solar flares and coronal mass ejections, CMEs, when the Sun's magnetic field lines become twisted or reconnected. It can lead to explosive releases of energy, producing solar flares and ejections of plasma into space. These events are often directed along magnetic field lines and can have significant effects on planets, including disrupting communication systems on Earth and creating auroras. The solar wind. The Sun's magnetic field extends far into space, creating a bubble known as the heliosphere. Charged particles from the Sun, known as the solar wind, travel along magnetic field lines and interact with planetary magnetic fields, shaping space weather and influencing planetary atmospheres. Many planets in our solar system, including Earth, have their own magnetic fields, which are generated by the movement of conductive materials in their cores. For Earth, this process is called the geodynamo, where the molten iron and nickel in the outer core create electric currents that generate a magnetic field. Earth's magnetic field plays a vital role in protecting the planet from solar radiation and cosmic rays. The field extends out into space, forming a region known as a magnetosphere, which deflects much of the solar wind. Without this protective shield, Earth's atmosphere could be gradually stripped away by solar particles, as is thought to have happened to Mars. Auroras. The interaction between Earth's magnetic field and the solar wind creates beautiful light displays known as auroras, the northern and southern lights. These occur when charged particles from the solar wind are funneled by the Earth's magnetic field toward the poles, where they collide with atmospheric gases, producing light. Magnetic reversals. Earth's magnetic field is not constant. Over geologic time, the poles have flipped in a process called a geomagnetic reversal, where the magnetic north and south poles switch places. These reversals happen irregularly and can have implications for planetary conditions. Although life on Earth has survived many of these flips, magnetic fields are not unique to Earth. Other planets, like Jupiter and Saturn, have extremely powerful magnetic fields. Jupiter's magnetic field, for example, is about 20,000 times stronger than Earth's, and its magnetosphere extends far beyond the planet, influencing its moons and trapping radiation in its intense belts. Jupiter's magnetosphere. Jupiter's magnetic field plays a key role in shaping its space environment. Its largest moon, Io, has intense volcanic activity that releases sulfur and oxygen into space, creating a plasma torus ring around the planet. The plasma interacts with Jupiter's magnetic field, generating powerful radiation belts and contributing to the planet's auroras. Mars and Venus. Not all planets have strong magnetic fields. Mars, for example, lost much of its magnetic field early in its history, which likely contributed to the loss of much of its atmosphere. Venus, on the other hand, has a weak-induced magnetic field generated by its interaction with the solar wind, but it lacks a strong internal magnetic dynamo like Earth's. Magnetic fields play a crucial role in the formation of stars. When a cloud of gas and dust collapses under gravity to form a star, the magnetic fields within the cloud can influence the rate and manner of collapse. Magnetic fields help regulate the transfer of angular momentum, which in turn affects the formation of a protostar and the surrounding accretion disk. Accretion disks. These are rotating disks of gas and dust that form around young stars or black holes. Magnetic fields within the disk help funnel material onto the growing star, and can also drive powerful jets of material away from the star's poles. Star-forming regions. Observations of star-forming regions, such as the Orion Nebula, show that magnetic fields are aligned with the structure of the gas clouds, suggesting that they play a role in channeling material and shaping the region's evolution. Magnetic fields are not confined to individual stars or planets. They also exist on much larger scales. Galaxies, including our own Milky Way, have large-scale magnetic fields that can influence the motion of gas and cosmic rays. Galactic magnetic fields. These fields are thought to be generated by the movement of ionized gas within galaxies, much like a dynamo. Galactic magnetic fields are often structured along the spiral arms of galaxies and can stretch across tens of thousands of light years. Cosmic rays. High-energy particles known as cosmic rays travel through space, and their paths are influenced by galactic magnetic fields. These fields can deflect cosmic rays, trapping them within the galaxy and preventing them from easily escaping into intergalactic space. Magnetic fields in galaxy clusters. On even larger scales, magnetic fields exist within clusters of galaxies. These fields may be generated by the motion of gas within the cluster or by the interaction of galaxies within the cluster. Such fields could influence the formation of cosmic structures and the distribution of matter on a grand scale. In some cases, magnetism becomes an overwhelming force in the universe. Magnetars are a type of neutron star with incredibly powerful magnetic fields, up to a quadrillion times stronger than Earth's magnetic field. These fields are so strong that they can distort atomic structures and generate intense bursts of gamma rays and X-rays. Neutron stars. Neutron stars are the remnants of massive stars that have exploded in supernovae. These stars have collapsed into incredibly dense objects, where their magnetic fields become compressed and amplified. Magnetars, in particular, have the most powerful magnetic fields observed in the universe, and they can cause starquakes, leading to bursts of radiation. Magnetic fields also interact with black holes, particularly in the region around their event horizons. In active supermassive black holes found in the centers of galaxies, magnetic fields in the accretion disk play a key role in powering the jets of high-energy particles that shoot out from the black hole's poles. Relativistic jets. These jets, which can extend for thousands of light years, are thought to be driven by the twisting and reconnecting of magnetic field lines near the black hole, converting rotational energy from the black hole or disk into the kinetic energy of the jets. On largest scales, the universe itself appears to have a magnetic structure. Observations suggest that there is a cosmic magnetic web, with filaments of magnetic fields threading through the large-scale structure of the universe, guiding the motion of galaxies and the flow of matter. This cosmic magnetism may have originated in the early universe, shortly after the Big Bang, and has been amplified over time by the movement of charged particles in galaxies and galaxy clusters. Magnetism is a fundamental force that shapes much of the universe we observe, from the formation of stars and planets to the structure of galaxies and beyond. Magnetic fields influence matter on every scale. While gravity governs the large-scale structure of the universe, magnetism drives many of the dynamic processes that give rise to the stars, planets, and cosmic phenomena that make the universe so fascinating. Understanding the role of magnetism in space is crucial for unlocking many of the mysteries of astrophysics and cosmology.